Hello and welcome to yet another lecture on Basic Electrical Engineering, paper code ESEE101. Myself, Prathita Roy, Assistant Professor of Dr. Sudhir Chandra Institute of Technology and Sports Complex, Department of Electrical Engineering. Today, my topic is EMF equation of a transformer, trans ratio, and equivalent circuit of transformer. Lesson objective. After any of this topic, student will able to understand the concept of EMF equation of a transformer, trans ratio, and equivalent circuit of transformer. So, in the previous class, we have mm, already gone through the transformer, what is the transformer, and about the conception of ideal and the practical transformer. Now we will do the EMF equation of a transformer. So when a sinusoidal voltage is applied to the primary winding of a transformer, a alternating flux that is phi m sets up in the iron core of the transformer that we have already seen. The sinusoidal flux that links the both primary and the secondary winding. The function of this flux is a sine function. So the rate of change of flux with respect to time is derived mathematically. The derivation of the EMF equation of the transformer is shown below. Let we are now considering that the phi m be the maximum value of the flux in Weber. F is the frequency of the supply in Hertz. N1 is the number of turns in the primary winding. N2 is the number of turns in secondary winding, and phi is the flux per turn in Weber. Now, let us take a cycle. Here it is seen that the flux that is changes from phi m to minus phi m in a half cycle, that is 1 by 2f second. It is clearly seen from that graph that the flux that is changing from plus phi m to minus phi m is the total time period, and time period t equal to 1 by f, what is the frequency of the supply. So it is changing in a half cycle of 1 by 2f seconds. So now, if we are applying the Faraday's law of electromagnetic induction, that is the EMF that is induced in the primary winding is given as E1 equal to minus D. We can write it in that way, that minus ddt of psi. Okay. So where the psi can be replaced by n1 into phi. Phi is the number of turns. Phi is the n1 is the number of turns that we have already done. That n1 is the number of turns in the primary winding, or phi is the flux in Weber. So we can write this u1 can be written as minus n1 ddt of phi. Here we that already know that phi is the function of the sine curve. So it's like if the AC supply, the phi became phi m sine omega t, where phi n is the maximum value of the flux. So now U1 became minus N1 into ddt of phi m sine omega t. So U1 became minus N1 omega phi m cos omega t. So U1 became minus N1 omega phi m sine omega t minus phi by 2. So it is clearly, from that equation, it is clearly given that the induced EMF lags by flux by an angle 90 degree. The induced EMF lags flux by 90 degree. So what is the maximum value of the flux induced EMF? The maximum value of the induced EMF is this part, N1 omega into phi m. This is the maximum value of the flux, N1 omega phi m. So where omega is known as the 2 pi f, the angular frequency, and this is omega equal to 2 pi f. So U1 max became 2 pi f in 1 phi m. So what is the RMS? That is called the root mean square value. Root mean square value is U1 and given as U1 max by root 2. So putting the value of U1 max in this equation 6, we get U1 equal to root 2 pi f in 1 phi m. Root 2 pi f in 1 phi m. This is the value of U1. So now we are putting the value of pi 3.14 in the previous equation. We are getting the U1 value equal to 4.44 if in 1 phi m. This is the general equation of a transformer. So same in case of that is U1 equal to 4.44 if in 1 phi m. Similarly, in case of the E2, it will become root 2 pi f into phi m, or E2 became 4.44 f into phi m. These two are the general equation. The general equation for a voltage that is induced in a transformer is 4.44 f n into phi m, where n is stands for the number of turns. If it is n1, then the voltage induced is called the primary voltage induced E1. If it is n2, it is called the secondary induced voltage. So we all know that the flux phi m equal to Em by Ai, where Ai is the iron area, the area of the iron, and Bm is the maximum value of the flux density. So E1 became from that equation 4.44 in 1 if B or BMAI volts, and E2 becomes 4.44 into F BM I1 A1 volts, AI volts. So E1 became 4.44 in 1 if BMAI, and E2 becomes 4.44 into F BMAI volts. It is that are the general equations of a transformer. Now we are dealing with the ratio of transformer, the voltage ratio, current ratio, and volt ampere ratio. So let us start with the voltage ratio. This is generally known to us E1 equal to 4.44 F phi m in 1, and E2 is the 4.44 F phi m in 2. So we are doing the E2 by E1. It is say N2 by N1 equal to K. This K is known as the transformation ratio. So E2 equal to K into E1, or K equal to N2 by N1. So this is called the transformation ratio. E2 by E1 equal to N2 by N1 equal to K, where K equal to N2 by N1 is known as the transformation ratio. Current ratio became V2 by V1 equal to I1 by I2, that is known to us, equal to K. And the volt ampere ratio, that is the kVA rating of the transformer, it became, in this case, V1 by V2 equal to I2 by I1 equal to K. This is known to us. So kVA rating becomes it is a multiplication of V into I. That is V1 I1 by 1000 equal to V2 I2 by 1000. Just called cross multiplication. This is called the volt ampere ratio. So we have learned about the transformation ratio, the volt ampere ratio, and the current ratio. So let us take an example. It is given that the maximum flux density in the core of a 240 by 2400 volt 50 Hz single phase transformer is 1 Weber per meter square. If EMF per turn is 8 volt, determine primary and secondary turns area of the core. So it is given that the PM, that is the maximum flux density, is 1 Weber per meter square. E1, that is the voltage at the primary side, is 240 volt. So E plus turn is means that is the EMF per turn is 8 volt and frequency is 50 Hz. So E1, the E1 became E turn into total number of turns. So from that particular equation, just putting those values of E1 and E per turn, we are getting the value of N1 equal to 30. So we all know N1 by N2 equal to E1 by E2. So N1 value we are putting 30, we know E1 equal to 240 and E2 equal to 2400. So from that equation, we are getting the value of N2 equal to 300. So just putting the value here, we are finding the value of E1 is given to 40. The equation is E1 equal to 4.44 phi m if into N1. So if value is given 50, N1 that we have just obtained 30. 4.44 and E1 is the 240. So phi m became 0.03636 Weber. So we have to find the Bm that we have. The Bm is given to us, that is Bm. So primary and secondary turns, that is N1 and N2 value we have already calculated. Now we have to find the area of the core. So Bm is not is equal to phi m by A. This is known as the flux density is known to us. So A became phi by Bm. So just putting those values, we are obtaining the value of A is 0.3636 meter square. So in this way, we can easily find the primary and the secondary terms of a transformer and also the area of the pole, where Bm value is given 1 by 1 per meter square. Now, we are dealing with some phasor diagram of a transformer on no load. So it is clear that this is the transformer where it is the primary winding, a voltage is supplied V1, and there is an secondary winding which is a no load winding. It is clear that this winding is the no load condition. So we are dealing with the transformer that is operating at no load. Before approaching to that, so this diagram is clear. A flux that is generated, that is linking between the primary and the secondary side, which runs into the voltage that is called the E1 and E2, and I0 is the no load component of the current. So before approaching to that particular portion, we are dealing with this one. We all know that V1 by V2, if we are considering that, say this one is N1 by N2, you can write it V2 by V1 as a, also you can write that V2 by V1 is in the form of N2 by N1. We can easily write in this way. Also, we can write V2. Say I am taking it is A, and it will be I2 by I1. You can write V2 by V1 also in that form of K that we have seen in order to understand this thing. So now, when I am going through in this part, we will obtain that the value of V1 became K into V2, and the value of I1 became I2 by K. So what is the Z1? Say the impedance of the primary side. Say Z1 is nothing but V1 by I1. If it is V1 by I1, then it will be became A square V2 by I2. Just putting those values. So Z1 became A square into Z2. That equation, we consider that this is called the refer to the primary side. Means refer to primary means refer to primary. That means that a secondary winding or secondary impedance is converting to the equivalent primary impedance. So you have to multiply with the factor called K square. And when the primary impedance is referred to the secondary, means with respect to the referred to the secondary means we have to multiply the primary impedance with k square 1 by k square. We have to multiply the primary impedance by 1 by k square for referred to the secondary. So this portion is generally known as, we are representing by it with the Z2 dash, the dash formation. And this is known as, this portion can be replaced by Z1 dash, means the dash conception is to refer to primary or refer to secondary. When I refer to primary, we have to multiply by k square. When you refer to secondary, we have to multiply by 1 by k square. Same in case of the current. This current, where I am telling that I, this current I2 into 1 by k, can I write? We can write it in the case of I2 dash, and we are considering that this is referred to the primary side. This current is referred to the primary side. It is I2, the secondary current, which is multiplied by the constant called 1 by k. This one. So in this way, we can refer to the primary or secondary side. So another conception is the transformer that is operating in no load, at no load condition. When the transformer that is operating at the no load operation that we have already seen. So we have seen that there are two, the equation, the transformer that is operating at the no load, that is the transformer that is operating at no load condition. So I can write here as the no load condition of the transformer. So when the transformer is operating at a no load condition, so it is clearly seen that this is called the primary side, and say this is called the secondary side. So here a voltage that is applied to the transformer, say V1, and this is kept open, and a no load component of the current that is I0. This no load component of the current I0 is flowing through the transformer I0, which in turn produces a flux. That is the flux phi that is routed through the core of the transformer. It's called the main flux. The flux that is known as phi, and this is kept at no load condition. This one, there is no load is connecting. So it is induce a voltage in the primary winding called this flux E1, and the secondary winding is called the E2. And this voltage is known as, there is a no load, so this voltage is known as V2. At no load, V2 equal to E2. At a no load, V2 equal to E2. Now if I draw the phasor diagram. So from that equation of the EMF equation of the transformer, we have already seen that the flux, that the induced EMF, both induced EMF E1 and E2 that we have already seen in our previous equation, that they are lagged behind the main flux by an angle 90 degree, where the applied voltage V1 is, now if I draw the phasor diagram at the, that we have already seen from the equation, that the E1 and E2, there is a part that is sine omega t minus pi by 2 for E1 and E2. When we do the transformer equation, EMF equation. So E1 and E2 are lagged by the main flux by an angle 90 degree. By an angle 90 degree. So let us take it as a main flux, IM. I'm taking it as an influx IM. And it's clear that the value of here E1 value is less compared to the E2, depending because uh, it is clear that when there is an it is a open circuited, that means there is a no load on the transformer. So there is a no chance of drop of winding resistance drop or the drop at the secondary side, because secondary winding is act as an ideal transformer. So there is no voltage drop in the secondary windings, and then we can write that V2 equal to E2, and the value is more compared to the E1. So here it is lagged. You see that it is lagging by an angle 90 degree, that we have seen from the equation, that it is lagging by an angle 90 degree with respect to phi m. So it is the E2 value that is more compared to E1, because here it is acting as an ideal transformer. Secondary side is secondary side, there is a no voltage drop, and this value is known as, up to that particular value, this is called E1. And the applied voltage, that is the V1, that we have seen, this V1 is always leading by the angle 90 degree with respect to the flux. So it is always leading by an angle 90 degree with respect to the flux. It is leading by an angle 90 degree, that is seen. So now there are two components of I0, that is the this part. This is called the no load current or exciting current, that lags behind the applied voltage by an angle say phi 0. We will see that. So it has two components. One is called the IM, which is known as magnetizing component. It is in phase with the phi m because it is responsible for producing the flux. So this is called the IM. And another is called the IC or IW. You can write it IC or IW, anything. So this is called another component of the current that is generally responsible to meet the hysteresis and the eddy current losses occurring in the to meet the hysteresis and the eddy current loss that is occurring in the core. So there are two components. One is called the IM, that is the magnetizing components, which is in phase with the phi m in order to generate this flux. And another is called the I mu or IC. We can write anything. I W or IC, we can write anything. This is generally responsible in order to meet the hysteresis and the eddy current losses occurring in the core of the transformer. So resulting of these two, which is known as I0, it is the no load component of the current or the or the or we have said that exciting current I0. And it is clear that it is lagged by the voltage V1, applied voltage V1 by some angle, and this angle is known as this angle. So this is angle value is known as phi 0. So it is lagging by some angle called the applied voltage V1, which is the phi 0. So this is the transformer equation, a transformer phasor diagram under no load condition, where uh, let where now a question will arrive that why E2 is more compared to the E1, because the number of trans is more In case of secondary winding compared to the primary winding, the number of trans are more in case of the secondary winding compared to the primary winding. We are considering that N2, that is the number of trans in secondary winding, is greater than N1. So that is why the E2 is greater than E1. E2 is greater than E1. This is the desired diagram at no load condition of the transformer. So we can write that IW or IC, that we can anything that we can say it is I0 cos phi 0. This one I0 cos phi 0 equal to IW, and IM equal to I0 sin phi 0. I0 equal to Im sin phi 0. It is responsible for producing the flux. The total value of the I0 will be given root over of IW or IC square, anything, plus Im square. So the no load power factor, that is no load power factor, can be found from that equation, that is phi 0 is nothing but from that equation, sin theta by cos sin phi 0 by cos phi 0, from that equation it will be tan phi 0 equal to Im by Iw, that is tan inverse Im by Iw, that is the angle, tan inverse Im by Iw, and taking the cos of that equation, that is finding the value of phi 0, and I0 phi 0 is that I0 cos phi 0 is that Iw, and I0 sin phi 0 is the Im. Taking the cos of that equation, we are finding the power factor. We are finding the power factor. So in this way, we are designing the no load working no load operation of a transformer. And this is the phasor diagram when the transformer is operating at no load. This is the phasor diagram when the transformer is operating at no load. While we are considering this one N2 greater than N1. So that is why E2 greater than E1. And at no load means E2 equal to V2, because there is no voltage drop in the secondary winding. And this flux, which is this component Im, is responsible for producing the main flux, which is link between the primary to secondary, which generate the voltage drop U1 and E2. And another is called the IW or IC, which is generally known as the current which is required to meet the hysteresis, and the eddy current losses that is occurring the core. So when a transformer is connected to a supply, there actually occurs a eddy current loss and the hysteresis loss in the iron core and appear as a heat. So when a transformer is connected to a supply, there actually occurs the eddy current loss and the hysteresis loss in the iron core and appear as a heat. This power is taken from the AC supply at primary side. The no load component IM is used. That the no load component, that is IM, is used to magnetizing the core. So there is no power loss due to this current. The current IM, that is lagged behind the applied voltage V1 by 90 degrees. So we are seeing that IM, which is in phase with the phi m and lagged by the applied voltage V1, is the V1, the applied voltage, by an angle called 90 degrees. So the another thing is that the product of IM and V1 does not represent active power. So this product is called the reactive power. So therefore, the input active power at no load, that is the input active power at no load P0, is V1 into IW, that is V1 I0 cos phi, is the input active power at no load cos phi 0, and the reactive power is given by W0 is V1 into IM, that is V1 I0 sin phi 0. This is called the operation at no load. So let us take the operation of transformer on load condition. Transformer on load condition. So we will discuss about the transformer on load condition. Means we are given load to the secondary of the transformer. So this is a transformer. This is the transformer construction. This is known to us. So we are given a load to the transformer. So again, we are considering that number of turns in the primary side is there compared to the number of turns in the secondary side. Secondary side has no number of turns. This is the primary side. So the applied voltage at the primary side is V1. Applied voltage at the primary side is V1, which in turn produces a current called I1. 1 stands for the primary side and 2 stands for the secondary side, and here it is a load is connected at the secondary side. Load that is connected in the secondary side. And there is a voltage called V2 here at the secondary side. And the secondary current, that is the I2. So here the induced EMF at the primary side is E1, and for the secondary side is E2. Now it will set up a flux, which is a main flux phi, main flux phi. So when a secondary is loaded, it will allow a flux to flow through that core, that is called the phi 2, in the opposite direction of, it will allow a flux, that is phi 2, to flow in the opposite direction of the flux depending upon the ampere trans in the secondary winding, it will allow a flux to flow that is in that opposite direction phi 2. So the resultant flux became phi minus phi 1. But the transformer, the main operating phi minus phi 2. So the main operating principle of the transformer is to maintain that flux phi a constant way, because same amount of flux must be linked between in between the primary and the secondary winding. But here the resultant flux becomes phi minus phi 2. So in order to uh, nullify the effect of phi 1, we have to produce another flux that is say called phi 1. There is theta 1, which is, so the main flux is theta. So if I load in the secondary side I2, depending upon the number of trans in the secondary side, depending upon the number of trans in the secondary side, it will produce a flux that is called the phi 2. It is in opposite direction of the main flux phi. So resultant flux became phi minus phi 2. So we have to adapt, or we have to develop a flux called phi 1, which is opposite in the phase of phi 2, and the magnitude is same as phi 2. So we are developing a flux called phi 1, which is opposite in phase of the phi 2, but the magnitude will be same, so that we can able to nullify that effect of uh, phi 1 and phi 2, and the resultant flux becomes phi. The main flux remains constant. So how we can do it? We just, depending upon the number of trans in the, only the primary side have we left. So depending upon the number of trans, the ampere trans in the primary side, that is I1 in 1, we are generating a flux that is called this one is in opposite direction of the phi 2, but the magnitude will be same as, so this flux is generally known as, this flux will given a value of phi 1. So the direction is the phi 2 direction in the yellow color that we have seen in this way, and the direction of the phi 1 is in that way. Direction of the phi 1 is in that way, and direction of the phi 2 is in that way. So because we are creating the phi 1 from the primary side, so value of the phi 1 is equal to phi 2 by adjusting the number of ampere turns, and it is clear that it will nullify the effect of phi 2, and the resultant flux becomes phi. Maintain the flux at phi. So now we are dealing with an transformer. We are dealing with an transformer equivalent circuit. It is clear from the transformer equivalent circuit is that from the transformer equivalent circuit, it is clear that this one, there is a resistance in the primary side of the transformer. There is a resistance and a reactance, that is Z1, which is, and this is the no load. From the no load component, we are finding that this part. So we are finding that this one from the no load component. This is I0, and this is the I0 have a two part. One is called the IC or IW, and another is called the IM, which is responsible for producing the flux. This is R0, and this is the X0. So this is the applied voltage V1, and this This is known as the total impedance Z1. This is R1 and this is X1. And here this is the induced EMF at the primary side. Depending upon the number of turns, it is called the E1. E1, and this current is known as I1, and this is called the I2. And this is generally the secondary part when it is loaded. Secondary part when it is loaded, that is responsible for producing the phi 2 that we have already seen. And any inductor is a combination of inductor and the resistance that we all know. This is R2, this is X2, this is R2, this is X2. The total is the Z2. The current that is flowing through the secondary is the I2. Part of this is the I2 dash, which referred to that. And this is the V2 voltage. And this is the load that we are dealing with. Load. And this is called the E2. This is the equivalent circuit of an transformer. This part is responsible for producing the flux, that is phi 1, this is phi 2, and this part is responsible for producing at no load operation. It's responsible for producing the main flux phi, where IM is the magnetizing component, it is responsible for producing the flux, and the second component, it is IW or IC, is the current. This current which is required to meet the hysteresis and net current losses occurring in the. This is the equivalent circuit of it. This is the equivalent circuit of a transformer. This is the equivalent circuit of a transformer. This is the equivalent circuit that we are obtaining from a transformer. Now, if I draw the phasor diagram on load, phasor diagram on load, phasor diagram of a transformer. Of a transformer on load condition. This is one of the main part. Is a phasor diagram of a transformer on load condition. It is found that now you are considering on lagging power factor. You are trying for the lagging power factor. Lagging. You are drawing for the lagging power factor. So This is generally known to us, this part, that is phi m, and we also know that phi m is always in phase with the phi m from the no load. This is the no load part, and this is IW. So this is called the IW. This part is called the IW. That we have already seen. The resultant is the I0 that we have already known. Now, another is called the V1 dash. So V1 dash, the voltage that is E1, which is in opposite to the V1 dash is nothing but the from the previous diagram we have seen that V1 and the V1 is opposite in direction. So V1 dash is analogous to minus V1. So minus U1. So you all know that U1 will be there. U1 will be there. Here U1 we have already done. So V1 is nothing but the minus U1. So it is V1 dash. So it is called the V1 dash. So another thing is that the I2. So I2 will be always lag. It is a lagging power factor. So I2. So this is one is the V2, the voltage V2, secondary voltage, and I2 will be always lagged by the voltage V2. So here it is called the I2. If it is I2, it is referred to the primary, that it will be, so say this is the I2. So if it is I2, so referred to the primary, I2 dash will be in that way. So for the better understanding, there is a V2 cell. And this one, same, that is the I2. That is I2. From this part to this part, this is the I2. This one. So I2 dash will be in opposite direction to the I2, referred to the primary. So we have seen from that these two will result the value of I1. That I1 from the particular graph we have, from the particular equivalent circuit that we have already seen, these two will result the this one, which is called the I1. The resultant of I0, and this is the I0, and resultant of I2 dash will be I1. So as this is I1, so we can write V1 dash plus I1 R1. There is the plus I1. I1 is this. So parallel to this is the I1 R1. So this is I1 R1. So I1 R1, and 90 degree from that it is called the, so I am just rub that particular part so it is easily understood by you. So 90 degree direction movement, it is called the I1X1, that we have seen in the primary side. So that these two resultant will cause the resultant of in this direction, that is the resultant of V1, is the V1, the resultant. So here it is I2. So if it is I2, then V2, it is I2R2. This is I2R2, and this is I2X2. So this part is I2R2, and this part is I2X2. secondary side. So the total part will be the E2. So this part, this this one V2 plus I2R2 plus I2X2. So it will be create a E2. And this is the direction of also the phi 2 also. So this is the phasor diagram of a transformer. Phasor diagram of a transformer. Phasor diagram of a transformer on load condition. Because E2 minus I2R2 minus I2X2 will be give the V2 value. Same. Uh, if I saw that equation V1 minus I1X1 minus I1R1 will give the U1 value. That is the minus U1 because it is opposing the V1. So V1, yeah. So the opposite to the U1, that is the V1, that is called the V1 dash. So this is the resulting result diagram of the transformer on load condition. So this part is we have already done. Load condition for the this is for the lagging power factor, unit power factor, and leading power factor. All will be the same. If I go through it, all will be the same. This is for the unit power factor. This is the lagging power factor that we have done, and this is for the leading power factor. So this part equivalent circuit of a transformer that we have already done. This equivalent circuit of a transformer that we have already done. Say this is the V1 minus I1R1 minus I1X1 is the V1. So that is why and we are writing U1 as a V1 dash, and that is why we have seen in case of the for that is one. This V1 minus I1 X1 I1 R1 is the V1, that is the V1 dash. And same here, that is E2 minus R2 X2 I2 R2 minus I2 X2 is the V2, and I1 is the summation of I0 plus I2, and I0 is the summation of IC plus IM. So that we have already done. This one, that is the I1 is the summation of I2 and I0, and E2 minus I2X2 I2R2 is the V2 value that we have already done. That is the I1 is the summation of I2 and I0 that we have seen, and E2 minus I2R2 I2X2 minus I2R2 is the V2 that we have already done. So this part we have already known that transferring from the secondary parameters to the primary side, that we have to multiply with the help of k square or 1 by k square for primary to secondary or secondary to primary. So let us, this one is the, say the equivalent that it is reflected from secondary to primary, so it is written as R2 dash and the X2 dash, that is the total Z2 dash, and the E2 dash, that is the secondary side, is reflected to the induced EMF is reflected to the primary side, that is E2 dash equal to E1, so ZL dash equal to ZL by K square. So in this way it is referred to the, we are dealing with the referred to the primary side, means the secondary impedance, secondary voltage, secondary current will be reflected to the primary. So that is why it is written as I2 dash. So it is R1 dash is K square by R1, X1 dash is K square by X1, Z1 dash is K square by Z1, U1 dash is K by U, K into A1. So that is, we have already done that. We are multiplying that in this way that R2 dash can be written as this one, that R2 is there, we are multiplying with K square into R2 is the R2 dash. So R1 resultant became R1 plus R2 dash, that is R1 plus K square into R2. So I2 dash became 1 by k into I2. That is with reflect to the primary, refer to the primary side. So x2 dash became k square into x2, that is x2 dash. Same thing is written here. So this is the continuation equivalent circuit will refer to the primary side here. So if I do this, refer to the primary side, it will clear that the refer to the primary side, the R01 can be written as R1 plus refer to the primary side k square into R2. That R2, the secondary resistance, is multiplied with the k square trans ratio. So this is known as R1 plus R2 dash. So same case in case of the x of 0, 1, that is x1 plus k square into x2, that is x1 plus x2 dash. Same I2, that is the current, that is I2 dash, which is written as 1 by k into I2. The voltage E2, the voltage E2, that is written as k into E1. The E2 can be written as with respect to the primary side, that the E2 dash, say I am writing E2, E2 dash can be written as k into E2. So in this way we are referred to the primary side. We refer to the primary side. That is the resultant that we have done. All these streets are referred to the V2 become V2 by K, that we are already known. So that is why we are referring to the primary side. This one that I have already told. So since the no load current is 1% of the full load current, the no load circuit is given here. So let us take an example that given a 6600 by 440 volt single phase transformer has a primary resistance of 2.5 ohms and a secondary resistance of 0.0 ohms. Calculate the total equivalent resistance with respect to the primary and secondary. So given that the values are R1 equal to 2.5 volt primary and R2 is 0.01 ohm. So K is given by 400 by 6600, that is 0.0606. So R2 dash is R2 by K square. Just putting those values, we are getting the equation 2.7225 ohm. R equivalent, that is R1 plus R2 dash, that is the summation of 2.5 plus 2.2775, that is 5.225. Then same in R1 dash equal to K square into R1. So we are putting those values. It is given 0.0606 whole square into 2.5, that is equal to 0.00918 ohm. So R E2, that is R2 plus R1 dash, that is 0.01 plus 0.00918, that is 0.01, 0.00918, that is 0.01918 ohm. That is one is referred to the primary and another is the referred to the secondary one. We have to multiply by the K square and another is the 1 by K square. That we have already seen. So today we have learned about the transformer EMF equation, trans ratio, and element the transformer equivalent circuit. Thank you.